Hello and welcome to Lecture 2 of Work and Energy in Electrostatics in Phys 1204. In this lecture we're going to learn about drawing and thinking using equipotential curves. As we saw in the last lecture, for a situation like this where we're moving this charge Q2 in the vicinity of this other charge Q1, during any motion along a path like this one from A prime to B that moves along a circle centered on Q1, the electric force will do zero work on Q2. And we know that because the electrical force acting on Q2 must point radially outward from Q1. And so it's perpendicular to the motion anytime we move it along a circular path, like this one from A prime to B, or this other circular path on this inner circle. So let's view Q2 as a probe charge. So we're going to use it to think about the potential in this region around Q1. We note that because zero work is done on it as it moves along this curve, that means equivalently in the system including both Q1 and Q2, the potential energy, the electric potential energy, does not change as we move Q2 along this circle. And so since we get the potential now by just dividing the potential energy by Q2, we see that the potential due to Q1 is the same everywhere on this curve from A prime to B, or on this inner circle. These are examples of what we call equipotential curves, curves along which the potential is the same everywhere. Let's think for a moment about contour lines on topographic maps. And the reason to think about contour lines is that if you don't already have an intuition about them, it's relatively easy to develop an intuition about contour lines. And any intuition that you have about contour lines can be carried over to equipotential lines because they work in basically the same way. So a contour line on a map shows a curve of constant elevation. In other words, if I were to start somewhere on this line, which is labeled 200 meters, and hike along it, then I would be hiking at a constant 200-meter elevation. I would not be going uphill or downhill as long as I followed the contour line. That means that these are lines of constant gravitational potential energy. Because I do not go up or down as I hike on this line, my gravitational potential energy doesn't change as I do this hike. Or equivalently, we could say that the work that the gravitational force does on me as I walk along this line is zero, because my path is perpendicular to the direction that gravity is acting. Continuing to think about reading topographic maps, there are some additional pieces of intuition we can get. Suppose I start at this point, and let's say I now hike in this direction, some particular distance. Now, suppose instead that I had started here, and I hike a similar distance in this direction. So there's a similar distance. Well, along this hike, I went from somewhat above 380 meters to, again, somewhere very close to 380 meters. So I've hardly gone up or down. Whereas here, I started somewhat above 300 meters on this contour line, and I've ended up below 100 meters. And so hiking the same distance, I went a long way down here, and very little way down here. This tells you, looking at those two regions on the map, that where contour lines are close together, the ground must be steeply sloped, because if the lines, which mark constant elevation, are close together, that means you can go a short distance and yet go through a rather large change in elevation. Also, if I'm standing here, then if I face this way, I'm facing in the direction along the hill, neither uphill nor downhill. If I want to face uphill, I would turn perpendicular to the contour lines. Or similarly, if I want to face straight downhill, I would turn perpendicular to the contour lines in roughly this direction. Note that what we're talking about here is a map showing values of a scalar. And so we don't need arrows, and these lines don't have little things like this. They don't have those because we're not showing anything with direction. Height is just height. It's a number. Also note that we cannot draw every contour line on a topographic map. Again, the map would just be covered in ink and wouldn't be useful. So the makers of this map have chosen to use 20-meter increments. You can see, for example, the 340-meter line and the 360-meter line. We could guess that the 350-meter line runs perhaps something like this, about halfway between them. We've already seen that the equipotential curves due to a single charged particle are circles. You don't know yet how to draw equipotential curves, but you will. Here are the equipotential curves due to a dipole. And let's compare them with contour lines in various ways. One thing we know already is that if we bring in a probe charge and move it along one of these equipotential curves, we know that the potential energy of the system doesn't change. That's the definition of an equipotential curve. Well, the reason it doesn't change, also, as we've seen, is that the electric field points perpendicular to the equipotential curve everywhere, and so the electrical force acting on our probe charge is doing no work. Well, that tells us that if we draw the field lines, they will be perpendicular to the equipotential curves everywhere. This is just like looking at the contour lines on a topographic map and realizing that if you want to face straight downhill, you need to turn perpendicular to the contour lines. So in other words, the field is always pointing straight downhill, if you want to think of it that way, in the potential. How do I know that it points downhill and not uphill? Because after all, I haven't labeled these equipotential curves. On the topographic map, there were labels on all of the lines in meters. These aren't labeled yet. Well, we do know that when we bring a positive charge in close to another positive charge, it has high potential energy, and its potential energy decreases when it moves over towards a negative charge. Since the potential at any point, say A, is just the electric potential energy of a charge we put there divided by the amount of charge we put there, that tells us that our positive probe charge is telling us that potential is high near this positive charge and low near this negative charge. And we know the field points from the positive charge towards the negative charge, and so the field is pointing downhill, or in other words, from regions of high electric potential towards regions of low electric potential. The contour lines on a topographic map are generally labeled in meters. If we were to label these equipotential curves, what would we label them in? Well, we can just do a unit analysis over here. Our potential is an energy, which must be in joules, divided by a charge, which must be in coulombs. And so those are the units of electric potential. Very similar to the newtons per coulomb that we measure a field in, right? Field is a force per unit charge. Potential can be thought of as an energy per unit charge. Unlike field, though, we have a name for this unit. This is the volt. You've probably been wondering when volts would show up. 1 volt is defined as 1 joule per coulomb. Now I could label these equipotential curves. Remember, though, that where the potential is 0 is an arbitrary choice. I'm going to arbitrarily choose this straight line halfway between the positive and negative charges to be the 0-volt equipotential curve. And so now, depending on the scale and the size of the charges, these other ones might go in perhaps increments of 10 volts, like so. Think about how charges tend to move in response to a field. If we put, again, a positive charge somewhere, then it will accelerate in the direction of the field, because the electric force on it is going to be in the direction of the field, and so it accelerates that way. Well, that means that positive charges will tend to accelerate from higher potential towards lower potential. And so positive charges have a tendency to move from regions of high potential to low potential. Similarly, negative charges accelerate in the opposite direction to the field, and so they tend to move from regions of low potential to high potential. It's as if you had different balls that you could roll around on a surface, and some of the balls would behave like regular balls and tend to roll downhill. Those would be the positive charges, but you would have some other odd balls that would tend to want to roll uphill, like the negative charges. I did warn you that we would see some more really dumb conventions, and here's one of them. Note that for electric potential, the symbol we use by convention to represent it is V. And the units of electric potential are volts, and the symbol we use for volts is V. Well, that's just a formula for confusion, so watch out for it. I will tend almost always, when I'm writing a symbol for a potential, to put a subscript on it that's indicating something like where the potential is measured, so that it's easier to tell my V's standing for the quantity potential from my V's standing for the units of potential. Here is a positive plane of charge seen from the side, and we know that it produces a uniform field which is perpendicular to the plane everywhere. Well, remember that that field is perpendicular to the equipotential curves, and so the equipotential curves aren't really curves here, they're lines, because they must be perpendicular to this field everywhere, and the only way to make that happen is if they're straight lines which is parallel to the plane. Note also that we know this field is a uniform field, and so because how far apart the equipotential curves are tells you about how strong the field is, we know that these will be equally spaced lines. And I've said this is a positive plane of charge, so this potential would be high near it. I'm just going to make something up like 100 volts near it, falling off as we move away from it. However, note that this is a two-dimensional picture. Fields and the things producing them are generally three-dimensional. And so here's an attempt at a three-dimensional drawing of a plane of charge, and the equipotential curves, or lines, are not curves or lines at all. They are, in fact, surfaces, which would be planes parallel to the plane of charge. Think about a charged conductor. We've already seen that the charge on a conductor is always on the surface. And we've also seen that the E field inside a conductor in equilibrium is zero everywhere. Well, the equipotential curves have to be perpendicular to the E field, and their spacing is related to how strong the E field is. Closely spaced means large field, and so a zero space means the equipotential curves are infinitely far away from each other. Or in other words, this is a region of constant potential. And so this is in general true, that for any conductor in equilibrium, the potential is the same everywhere inside the conductor.